Assalamualaikum warahmatullahi wabarakatuh. My name is Syahira binti Muhammad Salleh. This is a group presentation for Electronics DAE 21303. For the group members, we have me, Syahira binti Muhammad Salleh, and Ahmad Usamah bin Nazar. Okay, for the main components, we will discuss and presenting today for this video is BJT characteristic, number 2 JFET characteristic, and the last one comparison and exercise as amplifier application. Okay, so I'm gonna present about the bipolar junction transistor BJT. Introduction. A bipolar junction transistor BJT is a type of transistor that uses both electron and electron holes as a charge carrier. In contrast, a unipolar transistor such as a field effect transistor use only one kind of charge carrier. A bipolar transistor allows a small current inject at one of its terminal to control a much larger current flowing between two other terminals, making the device capable of amplification or switching. BJT use two junctions between two semiconductor types, N-type and P-type, which are regions in a single crystal of material. The junction can be made in several different ways, such as changing the doping of the semiconductor material, as it is grown by depositing metal pellets to form a low junction, or by such methods as diffusion of N-type and P-type doping substance into the crystal. The superior predictability and performance of junction transistors soon displays the original point contact transistor. Diffuse transistor, along with the other components, are elements of integrated circuit for analog and digital functions. Hundreds of bipolar junction transistor BJT can be made in one circuit at a very low cost. Okay, we move to the next point. Bipolar junction transistor BJT structure. The BJT is manufactured with three semiconductor regions that are doped differently. These three regions are known as the base, collector, and emitter. The base region is lightly doped and it is very thin compared to the collector and emitter region. The collector region is moderately doped while the emitter region is heavily doped. BJT can be an NPN or a PNP type. The NPN type consists of two N regions separated by the P region. The base region is the P-type material, while the collector and emitter regions are N-type material. In PNP type, the transistor consists of two P-type regions, the collector and emitter, separately by N-type base region. Regardless of the type, a BJT has two PN junctions that must be correctly biased with an external DC voltage to operate properly. One of these junctions is called the base emitter junction, connecting the base and emitter regions, and the other one is base collector junction, connecting the base and collector region. Basic BJT operation. In order for a BJT to operate as an amplifier, its base emitter junction must be forward biased, while the base collector junction is reverse biased. This means that an NPN transistor and a PNP transistor are backwards compared to each other. And as mentioned earlier, the emitter region is heavily doped. So in N NPN transistor, the N-type emitter region has a very high density of free electrons, while a PNP transistor, the P-type emitter region has a high density of holes. Okay, this is a NPN BJT bias arrangement. At this point, note that current and electron flow are backwards, which may cause confusion. Since the base emitter junction is forward biased, free electrons from the emitter regions easily cross the base emitter junction and go into the very thin and lightly doped p-type base region. The p-type base region is just lightly doped, which means that it doesn't have that many holes in it. In this case, only a small percentage of the free electrons from the emitter region can recombine with the hole in the base region. The small number of free electrons from the emitter region that recombine with the hole in the base region move through the base region as valence electron. But when they leave the base region and move through the metallic base lead, they become free electron and produce the external base current, which then goes out through the metallic lead into the external circuit and then eventually return to the emitter region. Okay, this one is PNP BJT bias arrangement. Okay, as I try to understand it, reversing the external bias voltage will forward bias the base emitter junction of a PNP transistor and reverse bias the base collector junction. Since the base emitter junction is forward biased, holes in a emitter region can move through the base emitter junction and enter the base region. At the same time, electrons in the base region can also move into the emitter region. Inside the PNP transistor, the emitter current is due to the movement of holes from the emitter to the base region. But externally, emitter current is due to the movement of electron from the emitter region to the positive terminal of the external bias voltage. The base current produced in a PNP transistor is due to the movement of electrons from the external bias voltage into the base region. Since the base region is just lightly doped, only a small number of electrons in the base region recombine with the hole from the emitter region, and the rest of the holes move into the collector region. Internally, this movement of holes into the collector region produce the collector current, but externally, the collector current is the flow of currents from the external bias voltage into the collector region. Okay, BJT configuration. As the bipolar transistor is a 3-terminal device, there are basically 3 possible ways to connect with the electronic circuit with one terminal, being common to both the input and output. Each method of connection responding differently to its input signal within a circuit, as the static characteristic of the transistor vary with each circuit arrangement. As you can see, we have 3 terminal. First one is common base configuration. It has voltage gain but no current gain. The second one is common collector configuration. It has current gain but no voltage gain. And the last one is common emitter configuration. It has both current and voltage gain. The common base configuration. In this configuration, the base connection is common to both the input signal and the output signal. The input signal is applied between the transistor's base and the emitter terminal. The corresponding output signal is taken from between the base and the collector terminals. This type of transistor arrangement is not very common due to its unusually high voltage gain characteristic. Its input characteristic represent that of a forward bias diode, while the output characteristic represent that of an illuminate photodiode. The common base circuit is generally only used in a single stage amplifier circuit such as microphone, preamplifier or radio frequency amplifier due to its very good high frequency response. The next one is the common collector configuration. In the common collector or grounded collector configuration, the collector is connected to the ground through the supply. Thus, the collector terminal is common to both the input and the output. The input signal is connected directly to the base terminal, while the output signal is taken from across the emitter roots resistor. This type of configuration is commonly known as a voltage follower or emitter follower circuit. The common collector or emitter follower configuration is very useful for impedance matching applications because of its very high input impedance in the region of hundreds or of thousands of ohms, while having a relatively low output impedance. Okay, the last configuration is common emitter configuration. In the common emitter or grounded emitter configuration, the input signal is applied between the base and the emitter, while the output is taken from between the collector and the emitter. This type of configuration is the most commonly used circuit for transistor-based amplifiers and which represents the normal method of BJT connection. The common emitter amplifier configuration produces the highest current and power gain of all the three bipolar transistor configuration. This is mainly because the output impedance is low as it is connected to a forward bias PN junction, while the output impedance is high as it is taken from a reverse bias PN junction. We have discussed for n available of BJT, so we choose BJT PNP 2N2907A. It is a small signal switching transistor. So, one of the manufacturer is ON Semiconductor. If you want to search more about the ON Semiconductor, you can search on this website. Okay, as you can see, this is a official and provided datasheet from ON Semiconductor. This is a 2N2907A small signal switching transistor. This is a PNP silicon. Okay, and they also provide a few graphs. Here, as you can see, the first figure 1 is DC current gain. The second graph is base emitter saturation voltage. Figure 3, collector emitter saturation voltage. Figure 4, base emitter voltage. Figure 5, collector saturation region. Figure 6, input capacitance. Figure 7, output capacitance. And the last one is current gain bandwidth product. So that's all from me.
Okay, Assalamualaikum warahmatullahi wabarakatuh. My name is Ahmad Usamah bin Nazar. So today I would like to present about junction field effect transistor, JFET. Okay, first introduction. JFET is a junction field effect transistor that is formed by the diodes with the junction of PN. The conduction in the FET because of the type of channel formed between the terminals defines the JFET. The JFET is classified as N-channel and P-channel. These are symbols that define the difference in their functionalities based on their arrow indication. The arrow indication determines the flow of current when the gate and source terminal is forward biased. N-channel JFET device furthers. A small bar of extrinsic semiconductor materials N-type is taken and it is 2 ohmic contacts are made, which are the drain and source terminals of FET. Heavily doped electrodes of P-type materials form P and type junctions on each side of the bar. The thin region between the two P gates is called the channel. Since this channel is in the N-type bar, the FET is known as N-channel JFET. The electrons enter the channel through the terminal called source and leave through the terminal called drain. The terminals taken out from heavily doped electrodes of P-type material are called gates. Usually, these electrodes are connected together and only one terminal is taken out, which is called gate. Voltage current characteristics of N-type. The figure shows the V1 VI characteristics of a N-channel JFET. The curve represents relationship between the drain current ID and drain to source voltage VDS for different values of VGS. P-channel JFET device features. The device could be made of P-type bar with N-type gate. The device characteristic of N-type of P-type JFET is similar. The only difference being that in N-channel JFET the current is carried by electron, while in P-channel JFET it is carried by holes. Voltage current characteristics in a P-channel JFET, in the source is positive with respect to the drain. Here the source is the source of holes which flow through the channel to the drain. The pinch off is achieved by making the source to gate voltage. Source to gate voltage negative, thereby reverse biasing the P-N junction diode formed by the channel and the gate. The figure shows the VI characteristic of P-channel JFET. Terminologies involved in JFET characteristics. Knee point. There exists a point in the characteristic curve where the variation of drain current with drain source voltage appears to be linear, but after this point, the linearity changes into a curve channel ohmic region. The region to the left of the knee point in the characteristic curve is the channel ohmic region. Pinch off point, the point in the curve above which the drain current does not increase further no matter how much we are increasing the drain to source voltage. This point is termed as the pinch off point. Pinch off voltage. The voltage at the pinch off point is termed as pinch off voltage because at this voltage current is completely turned to be constant. Drain source saturation current. The drain to source saturation current is the current which becomes constant or completely enters a saturation state. Okay, this available of JFET 2N5485. JFET 2N5485 is N-channel JFET designed for RF amplifier and mixer applications. This device will operate well in the VHF UHF frequency range. You can enter this link to know. Okay, this datasheet from Fairchild. Okay, let's see. Okay, at this you can see the picture and this is datasheet and calculation and also this. Okay, this example graph. And also this. Okay, that's all from me. Thank you.
Alright, we move to the last component that we have discussed. It is comparison and exercise as amplifier application. Here is the comparison table of BJT and JFET. For the first parameter, carrier, BJT is bipolar, while JFET is unipolar. As you can see the symbol, and device type, BJT is current controlled device, while JFET is voltage controlled device. Their input impedance, BJT has a low input impedance, JFET has high input impedance. Gain, BJT has high gain, while JFET has low medium gain. JFET consumes less power than BJT. For the noise level, JFET is low than BJT. Thermal stability, BJT is low than JFET. For the size, BJT is larger than JFET, The last one is application preference. BJT has low current application, while JFET has low voltage application. Here is the example amplifier circuit of BJT. Common emitter amplifier drives speaker with audio frequency signal. Since the microphone may produce voltage exceeding the forward voltage drop of the base emitter PN diode junction, a resistor must be placed in series with the microphone. Simulate the circuit with spice. The netlist is included in the figure below. As you can see here, after we simulate, the circuit will be like this. Alright, here is the example amplifier circuit of JFET. We have two circuits. It is cascode amplifier circuit and multiplexer. Okay, so that's all from me. For the last point, I pass to the Usamah. Thank you.
Okay, so I will continue from Syahira Salleh. I will continue about voltage divider bias for JFET and BJT. Okay, we can count the gate to source voltage is, and the formula, and the gate voltage is calculated using the voltage divider formula. Okay. The source voltage is determined using the following formula. Since in this case IS equal to ID, meanwhile the drain current can be expressed as this formula, and the other expression for the drain current is this formula. Graphical analysis of a JFET with voltage divider bias. Q point of a JFET with the voltage divider on the transfer characteristics curve is found by utilizing DC load line. The point at which the load line intersects the transfer characteristic curve is Q point. Q point stability, figure 6 to 15 illustrates Q point stability for a self-biased JFET and for a JFET with voltage divider bias. With voltage divider bias, the change in ID between minimum and maximum Q point is reduced because the slope of load line is less than for self-bias. Current source bias, the Q point stability of a self-biased JFET can be increased with connecting a BJT in series with the JFET in the BJT acts as the constant current source because its emitter current is essentially constant if VEE bigger than VBE. Voltage divider bias configuration. Previous configuration ICQ and VCEQ were function of beta, but beta is temperature sensitive and actual value is usually not well defined. Desirable to develop a bias circuit that is less dependent or independent of beta. Voltage divider bias configuration. Two methods to analyze: exact method and approximate method. Voltage divider bias configuration exact analysis. Consider the BE circuit loop using Thevenin equivalent network. Voltage divider bias configuration exact analysis. Consider the BE circuit loop. Voltage divider bias configuration exact analysis. Consider the CE circuit loop. Voltage divider bias configuration exact analysis. DC load line analysis. During saturation, if VCE is small, not 0 volt, can use this formula. And during cutoff, IB equal to 0. Okay, voltage divider bias configuration approximate analysis. Resistance Ri is the equivalent resistance between base and ground for the transistor with Re. Resistance between base and emitter Ri, beta plus 1 Re and beta Re. If Ri is much larger than R2, IB much smaller than I2 current. Current always seeks the path of least resistance. If accept this approximation, IB equal to 0 and I2 equal to I1, and R1 and R2 can be considered series element. This expression analysis only valid if BRE bigger or equal to 10 R2. Okay, last, for example, determine the levels of ICQ and VCEQ for the voltage divider configuration using exact and approximate techniques. That's all from me. Thank you.